Good morning, everyone. Frédéric probably needs no introduction, but nevertheless, I will just say a few words. I have known Frédéric for now nearly 30 years, so long, and it has always been a pleasure and a privilege to work with him. In fact, we have been very lucky to work during possibly the golden age of GRB physics, with many new discovery coming from new experiment space observatories. First, we had the first indications that GRBs were located at cosmological distances, and then were releasing a huge amount of energy. They are the brightest source in the universe. Then we had the confirmation that they are located from Bepo-Sachs, confirmation that they are located at cosmological distances. We had the first redshift and the discovery of the afterglow, and more recently, gravitational waves, association of a short GRB with gravitational waves. So this is the last revolution that we are presently living in the study of GRB physics. And we have three active missions: SWIFT, Fermi, and SVOM, and Frédéric will talk a lot about SVOM. Frédéric has worked on practically all aspects of GRB physics: the prompt emission, the afterglow emission, the general properties, the statistical properties, the cosmological properties. He is also a very much appreciated professor at Sorbonne University and École Polytechnique, and I think that some of his past students are present in this room, and I know that Frédéric is very much appreciated by the students. So today you will focus on the SVOM mission. You will present the last results, and it's a busy time for you. I know that, but also very exciting.
Thank you very much, Robert. And this is the opportunity to say that indeed I was very lucky in 95, 96 when I decided to start a PhD project under your supervision. And it's a long story, but a fruitful story. Thank you, Robert. So good morning, everyone. It's a pleasure to have the opportunity this morning to present the SVOM mission and to show some early preliminary results. So I will start with an introduction on gamma ray burst. Then I will present SVOM, and then I will present our first results with some prospects. To explain what are gamma ray bursts, this old GIF from the 90s is still extremely useful. You recognize immediately the gamma ray sky in galactic coordinates with the diffuse emission of the galaxy and a few point sources which are supernova remnants. And suddenly, a source outside the galactic plane becomes extremely bright in gamma rays. You see that at the maximum, the detector saturates. It lasts for here about 10 seconds. With a variable light curve, it's extremely bright. And now that we know, as Robert just said, that these events occur at extragalactic distance, we know that these phenomena are the brightest electromagnetic phenomena known in the universe. They are not the brightest because most of the BBH detected in gravitational waves are even at least a factor of 10 brighter, just that gravitational waves are much harder to detect than photons. So I have tried to summarize the main observational facts. There are two main episodes of emission. So initially, we detect gamma ray burst with their soft gamma ray emission. This is a so-called prompt emission. It's short. It's highly variable, as shown on many examples like this one. It's short, but in practice, the duration covers several orders of magnitude. The shortest gamma ray bursts are a few milliseconds long. The longest gamma ray burst can be several hundreds of seconds. And the distribution of duration is bimodal with two groups, so-called short and long gamma ray burst. And we know today that it's a similar physics at work, which involves an ultra-relativistic outflow, but with different classes of progenitors and initial events to produce a compact source releasing this ejecta. And probably most of the long gamma ray bursts are associated to so-called collapsar, a particular class of core collapse of massive star at the end of their evolution. And most of the short GRBs are related to merger of binary neutron star systems. There is a great diversity of light curves. On the other hand, the spectra are non-thermal. So clearly, gamma ray bursts are cosmic accelerators with high energy emission produced by particles accelerated in shocks or in reconnection events or similar mechanism. And there is a very strong spectral evolution during the gamma ray burst, and the physical origin of that is still highly debated. And there is also a huge diversity of the gamma ray burst population. I have mentioned the two main classes, but in practice, when we look also at the spectral properties, there is really a lot of different classes or subclasses. And today it's a really fruitful period with many different probes of that. And probably we are starting to understand that there is a continuum of event from the most standard classical core collapse supernova to the most classical long gamma ray bursts with a great variety of intermediate transients in between. Following this prompt emission, there is a so-called afterglow, which is detected typically in X-rays, optical, and in some cases radio, and in some cases at very high energy. So here you have example of X-ray light curve in a log-log diagram. Here, this is the end of the prompt emission, and then you see a very early steep decay. It's often some kind of plateau phase, and then a power law decay. You see that timescales are still short. It means that even for the afterglow, we have to react extremely rapidly if we want to catch the afterglow. And what is especially difficult is to catch the afterglow in continuity with the prompt emission. And the first satellite which succeeded to do that efficiently is SWIFT, and SVOM is also doing that quite efficiently. And once we have the afterglow, not in X-rays like in this plot, but in optical, thanks to this good quality spectrum, we can identify either absorption line is the afterglow or emission line is the spectrum of the host galaxy and measure the redshift. And we have now a large sample of gamma ray bursts with measured redshift covering a very large range. We have a few gamma ray bursts above Z equals 7. The record is at 9.3 with a photometric redshift. And when we deduce the corresponding gamma ray energy released in a gamma ray burst, so it's a so-called isotropic equivalent energy because it's computed assuming that it's radiating the same way in all directions. And in practice, as it involves a relativistic jet, the emission is beamed in the direction of motion. But you see the numbers 10 to 51 to 10 to 54, and I should even say 10 to 55 for a recent monster. It's really impressive. Remember that the kinetic energy of a supernova is typically 10 to 51 erg. That's why we say that these are the brightest phenomena, electromagnetic phenomena in the universe. So I won't have time today to discuss in detail the physics of gamma ray bursts because I want to focus on SVOM and our first observation. But just very rapidly, an initial event, typically collapsar or binary neutron star merger, leads to the formation of a new compact source, a black hole, but there are also many discussions about neutron star with rapidly rotating magnetars, probably some material around accreting, a relativistic ejection. We don't have any electromagnetic signal from this phase. It's completely opaque, but we can have information with gravitational waves and neutrinos in the future. Then at large distance, the ejecta becomes transparent to its own radiation at the so-called photospheric radius. And this is where you can expect radiation to be produced. The prompt emission is due to internal dissipation in the jet itself. And there are many possibilities which are highly debated. Either it can be dissipation below the photosphere or above the photosphere, two very different classes of models. And for the dissipation mechanism itself, there are several ideas, but the two main ideas are either shocks, so-called internal shocks, a model on which we have worked a lot at IEP, or magnetic reconnection. And then later, initially, the outflow does not fill the ambient medium because it's such a huge energy, but at some point, it starts to feel that it's not vacuum, but that there is the circumburst medium, and it starts to decelerate. It produces a strong ultra-relativistic shock in the external medium, and the shocked external medium radiates what we see as the afterglow. And the fact that the afterglow is initially more in X-rays and bright and then decays rapidly and goes towards larger wavelengths is just a signature of the deceleration of the outflow. I could spend 1 hour on all the open questions related to this scenario. I have described what is the basic scenario on which everyone agrees. But then if you look in details to each step of this scenario, hot debate. And I hope that SVOM will contribute to eliminate some of these ideas and favor some others. I would like to mention a few recent advances in gamma ray burst studies. One is the most famous one, already mentioned by Robert, the multi-messenger event 170817, with simultaneous observation in gravitational waves and 2 seconds later gamma rays. So here we have really a direct association between a binary neutron star merger detected in gravitational waves and a short gamma ray burst. A kilonova in association, you see on a 1 week scale the decay of the dose and the change of color from blue to red. This emission is produced by an ejecta following immediately the merger, where the rapid neutron capture process leads to the production of new radioactive elements. And then the ejecta evolves with some heating terms due to radioactivity and some cooling due to the expansion and radiation. It's a similar physics to the physics of supernova ejecta, but in a very different regime. And the timescale is much shorter and the luminosity is much weaker. It's difficult to catch. In this case, the afterglow is very peculiar compared to what I have seen before, with a very slow rise for more than 100 days and a decay. And in fact, just for the physics of gamma ray burst, this event was really interesting because it's a very close event at 40 megaparsec. And for the first time, we see it completely off axis because the trigger was quite different, in fact. And in principle, if we had only a highly relativistic jet, we should not see anything initially due to the relativistic beaming. We should see nothing. And suddenly, due to the progressively, I should say, due to the deceleration, the relativistic beaming is less and less efficient. And at some point, your line of sight enters this cone. And it should have a sharp rise and then the decay. But it's not at all what we see. And the interpretation, and here you have an example with a nice light curve produced by Clément Pelloin here at IEP. The idea is that the core jet is surrounded by some kind of mildly relativistic, mildly energetic material that we detect for the first time due to the off-axis line of sight. And so initially we see this material on the line of sight, and due to the deceleration, we explore more and more region of the jet until the core jet at the peak and then the decay. So these are these two contributions. So it was really a very important advance for the understanding of gamma ray burst jets. There are many other results with this event. Other recent observation, now we detect a few gamma ray bursts in the TV range with S, MAGIC, or LASSO. This is very interesting because for the first time in the afterglow phase, there are hints of a two-component spectrum, probably synchrotron and synchrotron self-compton. So to constrain the physics of particle acceleration and radiative processes in these sources, it's extremely important. And something else which is really impressive is this very peculiar case, a gamma ray burst which occurred at the end of 2022. It's intrinsically an extremely bright gamma ray burst, the record 10 to 55 Hz for the isotropic equivalent energy. And in addition, it was at a quite small redshift for a gamma ray burst. So this is extremely bright. And it has been followed by many, many instruments. But among the most important observations, it has been detected by LASSO with thousands of photons in the TeV range and the highest energy photon at 13 TeV. Here really it's a very, look at the light curve. In fact, all the satellite triggered on this small precursor, and then there is this emission for hundreds of seconds. And the LASSO observation starts here. To understand the physics of the emission in such extreme cases is extremely interesting. And for the first time, there is an emission line at 10 MeV, which is detected in the gamma ray range. And Muad, who is somewhere here, is working on that in the context of his PhD. And also, as I already said, recent events show that the classification in terms of short and long is too simple and that the reality is more complicated. And just to give an example, usually people have in mind short gamma ray burst binary neutron star merger, long gamma ray burst collapsar. But recently, there are several cases. This one is a very nice case of a long gamma ray burst with a kilonova associated, which in principle is the signature of a binary neutron star merger. And so many debates about the origin of this emission, which somehow says something about the post-merger physics and the various possibilities for the ejection. So I will stop here for this introduction. I'm frustrated to not discuss physics, but in practice, if you want to know more, there are many colleagues here at IAP that can answer your question. So we are several to work on gamma ray burst physics at IAP. Some of us did not change our picture since the 18th. But you see that we are well prepared for the SVOM era because we cover all the steps in this general scenario. And in fact, we are not just interested in understanding the gamma ray burst physics, but we are also interested in the population in general, understanding the progenitor, and even use gamma ray burst to probe the distant universe. And if you want to know more, you should ask Susanna, for instance. Okay, so I'm sorry, as I could not show equations, I have shown pictures. So now I move to the main topic, the SVOM mission. I should say that not most, but many of the slides I will show are taken from two presentations made last week at the SWIFT 20 conference for the anniversary of the SWIFT mission by Bertrand Cordier, the PI, French PI of SVOM, and me, with the first results of SVOM. So I did not put on each slide when it was taken from that, but this is clear. So SVOM is a collaboration between China and France with two PIs on both sides, Jian Wei and Bertrand Cordier, and with many labs involved. And you see that on the French side, there are many labs, included, of course, the Institut d'Astrophysique de Paris. And we have also partners in Mexico for a follow-up telescope and in UK and Germany for the X-ray telescope on board SVOM. SVOM was launched on June 22 last year from Xichang in China. Several of us were there. And in fact, it worked. The launch was successful. And I must say that it's quite impressive to be in front of a launch. We were, in practice, the Chinese standards are not exactly the same, so we were at 2 kilometers from the launch site, and it's impressive. And we were completely euphoric after that. Jessie is here, I'm here. Okay. So SVOM has just finished the commissioning and validation phase, and it will enter this month the normal scientific operations. That's why most of the results that we show are really preliminary. So SVOM is composed of many instruments in space and on ground to detect gamma ray bursts and other high energy transients. So on board, it starts with two large field of view instruments, ECLAIR and GRM. ECLAIR is a coded mass telescope with a low energy at 4 keV. This is very new. The coded mass telescope on board SWIFT has a low energy threshold at 15 keV. So it's really a great progress. And the advantage of the coded mass telescope technique is that not only it detects gamma ray bursts, but it can localize them within a few arc minutes. GRM has a larger field of view, but can detect without localization. And the one great interest is to increase the spectral coverage of the prompt emission up to a few MeV. So with that, we have an excellent coverage of the prompt emission. So you can see the real instruments here, ECLAIR and GRM. So GRM is made of 3 detectors to cover a large field of view. So here you don't see the coded mask, but the mask is here. So you know the technique. The idea is to sacrifice part of the signal to be able to localize. So what you measure on the detector plane, which is here, is not directly what you receive from the sky, but it is the shadow of the mask illuminated by the sky. And from the position of the shadow, you can reconstruct the position of the source. This is such images. And this is how you localize gamma ray bursts within a few arc minutes. But of course, you lose maybe 35% of the signal because of the mask. So both instruments work very well. We know that after the commissioning phase. Then once it's localized, the localization is computed on board. And if you are above a certain threshold, there is an automatic slew of the satellite. Yes, I should show it with my Lego model. So Eclair, GRM. So, oh, a gamma ray burst. Ah, but no, now that I have computed the localization, it's here, slew, okay? And so once we have slewed, we are on axis for all instruments and including two new narrow field of view instruments, MXT in its rays, 0.2 to 10 keV, and VT invisible. So both instruments work. We have some highlight problems with MXT, which reduces a little the duty cycle compared to what was expected. But outside that, it's working very well. Compared to Swift, which has also two follow-up telescopes on board, MXT is less sensitive than the X-ray telescope on board Swift, but VT is much more sensitive than U-Bot on board Swift. So it's very complementary. So here are the two telescopes, MXT here and VT here. And I should have mentioned that VT has two filters, a blue and a red filter, which is sometimes quite useful. In addition to that, we have made a choice with SVOM, which is to have an anti-solar pointing. It means that the sun is here. I need energy. And we look in this direction. It means that if we detect a gamma ray burst, it's night on the Earth, and we can immediately follow up with ground-based telescopes. So it's a good idea. But there is a cost. And the cost is that once per orbit, we have the Earth in the field of view. So we lose some gamma ray burst, but we can detect the afterglow very rapidly and characterize very rapidly the gamma ray burst we detect. It is the idea. So we don't try to have the highest number of gamma ray bursts, we try to have the highest number of well-characterized gamma ray bursts. So this is illustrated with this view. And in addition, as we need to react very rapidly, we need to transmit the information very rapidly to the ground. And it is done with these two VHF antennas. And there is all on the ground, all along the orbit, about 40 VHF stations to receive data in real time. So here is the real current status of the VHF network. You see that the coverage is really good. There are still a few gaps, especially in the Pacific. But when we are not in a gap, the median delay to receive this early data is less than 8 seconds. So it is really excellent. Of course, it's not the full data. We don't have all events, etc. It's really what is necessary to validate and classify the early alert to inform everyone. And later, with another the so-called X-band channel, we receive all data from the satellite. And especially when we are in a gap, we can use another method to communicate in real time with them, which is the Beidou system, which is let's say the Chinese GPS. What is the goal of transmitting this information in real time is, of course, to react with other instruments. And we can do that already with SVOM instruments because we have 3 instruments on ground for SVOM, but also with many partners. So for the SVOM ground segment, we have a large field of view, but with a moderate sensitivity optical instruments called GWALC. The idea is that if we are lucky to catch the prompt optical emission in some cases, and we have 2 robotic telescopes with larger mirrors to catch the afterglow, a Chinese one and a French-Mexican one, which is in Mexico. I should say that for this one, in less than 1 year, we will have a near-infrared camera. in addition to the present instruments, which is of course interesting for the highest redshift gamma ray burst. And this is, I think, not a up-to-date picture of all the partnerships between SVOM and other instruments to organize the follow-up. And you can imagine how it is difficult to have such an organization with an agreement for each partner, etc. It's a really complex system. Okay, so here are some summary of the capabilities of SVOM. When we are not looking at gamma ray burst, there is a general program. I won't discuss too much the general program today, but if you are interested, don't hesitate to discuss. You know now the properties of the instruments, and SVOM is open to discussion, to participate, to observation. And in addition, SVOM is well adapted also for TO observation, either on our own events or with external alerts. This is what we were expecting before the launch, typically 1 TO per day. No, sorry, it's written here, 1 TO per day. So here you have the idea of the balance between the various programs. But in fact, today we know that we do much better. We have several TOs per day. Most of them, 2/3, are to follow SVOM gamma ray burst on the long term, because as VT is very sensitive, we can follow the afterglow for a long time. And 1/3 is to follow up external GRBs, mostly from SwiftMat, but also from Einstein probe. So I will illustrate how it works on one example. So GRB 250205A, so a burst occurring in February, on the 5th of February. It was the first one of the day. So it starts with the detection and localization by eclair, localization within 4.5 arc minutes in this case. And you see here the image with the point source. And here it's not a final image. This is typically the kind of information we get from the early VHF data, the quick look analysis. And here it is the same. This is a quick look analysis of the light curve in GRM. And this is an automatic pipeline. You see that works very well, because even with the slew, there is an automatic adjustment of the background model to detect the properties of the gamma ray signal above. 20 seconds later, it triggers the slew of the satellite. You can see it on this navigation plot. Here, this is the field of view of eclair, the field of view of GRM. Initially, the gamma ray burst was there. And after the slew, 132 seconds later, it is in the center of the field of view. That's why we can observe with MXT and VT. You see here the position of the gamma ray burst in the field of view of eclair. At the end, we are in the center. This is the opportunity to say that these plots, which are obtained with a quick look analysis pipeline for eclair and GRM, is the result of the work done at IAP in collaboration with LUPM. And so it's worked very well, this automatic pipeline. In 80% of cases, we have a result which works. And in the 20 other cases, an instrument scientist can reprocess in a few minutes and get a better result. And this is the opportunity to thank all the engineers who have worked on that. So in the past and today, I think they are here. Guillaume is here and Felu is here. Yeah. So there is a lot of work behind such that. So now that SVOM has flued, we can start to observe with the follow-up instruments on board SVOM. So of course, it takes time to integrate the signal. But typically, you see 500 seconds after the trigger, we have the first observation ready from VT and MXT. So on this plot, these plots are typically plots we can produce from VHF data. It's not final data, it's quick look analysis. Here you see the initial error box from eclair, which is refined when we accumulate signal. And here, these are all the error boxes from MXT converging towards the final position. And here, this is an image we get from VT. So it's a very peculiar image, because if you look at it carefully, it's a 1-bit image. It's 0 on 1 or 1 in each pixel, but which allows to identify by comparison with catalog a new source at the same position here. Of course, knowing this small error box helps to identify the counterpart in the VT image. And so at the end, it means that now we have a position within 1 arcsecond. We started with 4.5 arc minutes. And then, of course, as VT is very sensitive, it can follow the source for a long time, and you see that we catch very well the afterglow in blue and red band. In this case, the behavior is quite the same in 2 filters, but sometimes we are more interesting behaviors. During this sequence, which is somehow automatic on board, as I told you, we receive VHF data, we process them, we validate the triggers, the products which are produced, and then we send information to the whole GRB community via the so-called GCN network. It's either a notice, something for a computer, or a circular, something for a human being. And typically, we will inform, of course, the trigger time, the localization, but also some characterization of the burst to explain why it is interesting to follow it up. And this has to be done extremely rapidly in the minutes following the alert. So there are a lot of scientists on duty to succeed to do that efficiently, especially in this early phase where we don't have a perfect knowledge of all our instruments. So we have experts on the trigger, experts on each instrument and pipeline, and a burst advocate to supervise the sequence. And so typically, each lab has weeks of shift to react on alert. And so at IAP, we have a team, a burst advocate team. I think that Michel also has not changed recently his picture on the annual. I'm very proud to say that after having started studying gamma ray burst 30 years ago, I'm now an observer because I emitted my first GCN circular in last February.
No, it first occurred very late in the evening, I think.
No. In fact, we were training together in my office because it was our first week as burst advocate. So Michel was there too, and Sarah Antier, who is collaborating to our group for this year, was also online with us. So it was an excellent training. Of course, once we have the alert on ground, we can react with a ground-based telescope. And in this case, the afterglow is detected by Colibri, the telescope in Mexico, 6 hours after the burst. It's a comparison with the catalog image here. But now we can do much better. Last night, the Chinese follow-up telescope was on the source 57 seconds after the trigger. So there is really a high potential for the early afterglow. It's just that we have to optimize the sequence, but it worked very well last night. You can imagine all the sequence to manage this result, 55, you have seen all the steps. So then the community also react, including some partners, and you see the sequence of other circulars produced by other collaboration. So here, it's an interesting case because you see that, for instance, Michel would be proud to say that there is a detection at OHP. You see that this burst is also detected by Fermi GBM and by Einstein probe. And you see all the support from the community in such a list. The redshift has been measured, in this case 3.6. And there is even a radio follow-up at the end. And what is also quite interesting is to note the fact that Swift is reacting. And in fact, we have a really nice collaboration with Swift because our instruments are very complementary. Our visible telescope is more sensitive, their X-ray telescope is more sensitive. And with that, we can have a really good coverage of the afterglow. So this is the sky map of the first detected events, including already quite a large number of gamma ray bursts during the commissioning and validation phase. I will provide some more detailed examples in a few minutes. But I would like just to stress out in more detail the fact that we are very lucky and there are really an excellent synergy between current missions. So SWIFT has been observing gamma ray bursts since 2004. And here the idea is that not only we have common triggers, which is of course interesting also for SVOM to calibrate our instruments, but SWIFT is reacting to SVOM alerts to follow our gamma ray bursts with XRT, the X-ray telescope on board SWIFT. And there is now an agreement, and since February, this is automatic. There is an automatic TO for SWIFT from SVOM following an eclair trigger. And SVOM follows SWIFT GRBs with VT, which is more sensitive. For Fermi, which has been observing gamma ray bursts since 2008, the synergy is a little different. Fermi cannot localize accurately gamma ray bursts. But on the other hand, it has a unique spectral coverage. And so here, what is really interesting for us is the sample of common triggers, and especially we hope, and we should have some examples in the duration of the mission, that we will have events detected by Fermilat, which is the only instrument existing today to detect emission above 100 MeV. And finally, Einstein probe, maybe you are less familiar with Einstein probe, but it is another Chinese satellite sent in January 2024. Einstein probe is an X-ray satellite, you see, with a wide field telescope and a narrow field telescope. And the narrow field telescope is much more sensitive than XRT on board, than MXT on board SVOM. So here again, two very important synergies. We have already a few common triggers with the WXT, and the advantage that SVOM can characterize them with all the follow-up we can do, which is not possible. I mean, Einstein probe does not have a visible telescope on board. And in addition, MXT, like SWIFT XRT, contributes to the follow-up of the X-ray afterglow of SVOM on the long term. So you see that geopolitics is difficult today, but in science, sometimes it works better. So last part, a few early results. So really, I stress the fact that these results have been obtained in the commissioning and validation phase. So we are still far from the optimal conditions. So we have already detected, I think the numbers are for 2 days ago. We have already detected 89 GRBs, and 1/3 of them are SVOM-only GRBs. 2/3 are common triggers with other missions, and both samples are very interesting. So this is related to our 2 triggering instruments that I have already presented. I can say a few more details. So as I told you, ECLAIR is a coded mass telescope, but in addition, the triggering mechanism on board the SVOM for ECLAIR is much complicated, much more complex than what was done in the past. It uses many combinations of timescales, energy channel, and sectors in the detector plane. And it allows to be more efficient to detect some less known categories of gamma ray bursts. So here is an example. This is a histogram of the timescale of the first trigger for the first 26 GRBs with ECLAIR. First trigger, or the trigger with the best SNR, which is the one giving the best position. And this is for the same burst, ECLAIR burst, the mean energy for this trigger, for these alerts. And you see that we have a very large fraction of events with very long time scale for the trigger, above 40 seconds. The highest time scale on board SWIFT is 20 seconds. And we have a significant fraction of events which trigger below 8 kV, which is not covered by SWIFT path at all. And this is very interesting. And in fact, it's probably related to the fact that a large fraction of ECLAIR gamma ray bursts are SVOM-only gamma ray bursts. So we probe a larger population, let's say. We explore less known populations, which are more difficult to detect with other instruments. We can start to make rough estimates of the rate of event. So for that, we take the apparent rate and we correct for the fact that in the first months, the fraction of time devoted to observation was much less than in nominal phase. So at the end, we expect at least 50 GRBs per year detected and localized by ECLAIR. So let's say the golden sample. But GRM, which has a much larger field of view, is more than 100 GRBs. But all GRBs detected by eclair are in the center of the field of view of GRM. So it means that usually when we have an eclair GRM, an eclair GRB, we have either GRM observation or a strong constraint on the high energy spectrum. So it is really a very interesting sample. And then, since the launch, we have an automatic slew only for half of our eclair GRBs, but the threshold for that has been lowered last December, and now we are at 80%. And of course, the slew is very important because this is the only way to catch the afterglow very early. But in cases where we do not have a slew, we can emit a TO and observe with our instruments maybe 1 hour later, but it's more difficult. And I think that this table is very encouraging. In fact, this is really the table we were looking for, and there is a lot of effort behind this table. So the idea is to show here, this is GRM only gamma ray burst, and the two other columns are eclair gamma ray burst, and the last column is the small sample of eclair gamma ray burst with an automatic slew. And I show in each line the fraction of cases where we were able to detect the X-ray afterglow, the optical or near-infrared afterglow, and measure the redshift. And of course, what we want to do, he has the highest fraction here to have a fully characterized sample. This is what we want to do. And you see that it's already very encouraging. Let's say that with Swift, it's less than 30%. We are already at 37% for the small sample for all eclair gamma ray bursts, but for the gamma ray bursts with a slew, which will be a much higher fraction of the total in coming months, we are already at 50%. And you see that there is a huge effort behind that because, of course, there are strong contribution of all SVOM instruments to manage that with the X-ray telescope and the visible telescope on board or on ground. And I will show that these telescopes can sometimes also provide very deep early upper limit. But especially for the X-ray afterglow, you see the strong support of Swift XRT and Einstein probe FXT, which are much more sensitive. So the collaboration works really very well. And the partnership, for instance, with several collaborations like Stargate is also very efficient. Here is an example of a case in this column, a GRM only gamma ray burst, but which is common with Swift BAT, and so SVOM can contribute also to the follow-up of such event. And you see how nice our VT light curves. We are much more sensitive than UVOT, so we can follow the afterglow for a much longer time. And you see that there is a really interesting physics behind this light curve. It's not just a simple power law decay. There is some variability, some rebrightening of flares. There is a lot to learn about the deceleration of the relativistic outflow with such observation. So we are very pleased with these numbers, but our goal is to have 2/3 of our eclair gamma ray bursts with a redshift. So there is still room for improvement, but we have identified many ways to improve that in coming months. I can maybe stress two aspects. We expect a lot for the automatic TOs we have now with Swift and Einstein probe. We have many ideas to improve the delay to identify the optical counterparts with VT and then announce the position much earlier. And we also expect to have near-infrared capabilities in coming months with the Colibri telescope. So we have only 11 gamma ray bursts with redshift, so it's still a small sample, but here is the histogram. You see that the peak is not so far from the peak of star formation in the universe, but probably slightly above, which is not a surprise for gamma ray burst. We are already sensitive to a broad range of redshift, and you see that we have even already a gamma ray burst above Z equals 7. It's the first one for the last 12 years. So, and we get it in less than 1 year, so can be optimistic. It's too early to know if there is a strong benefit of the low energy threshold of eclair, but JC here said in the past that we should expect such a benefit. So we will see. In principle, for high redshift, it's better to decrease the low energy threshold. So in this sample, rapidly, a few examples. We have already one well-characterized short gamma ray burst, so related to the binary neutron star merger scenario. So I can show you what it looks like. You see a very narrow spike of the order of 1 second. But what is very interesting is that it's not the first time, but in this case, we detect very well an extended emission following the spike. And this is something which is very interesting to characterize because it says, again, something about the post-merger physics and the various kind of ejecta we can have. So we can, thanks to our instruments, measure the spectrum of the initial spike with the GRM, and it's a hard short burst, very typical. And thanks to Eclair, we can follow the spectral evolution from the initial spike in red to the extended emission in black, and confirm that it's still non-thermal emission during this extended emission, but which is weaker and softer. So this is interesting, and in the future, what we would like to do, yeah, I should say that then the follow-up was not easy. You see that compared to a sample of X-ray afterglow with Swift, we are a quite weak case here, but still, thanks to our friends at Swift and Einstein probes, the afterglow was detected, which then allowed it to detect the optical counterpart, the host galaxies, the redshift, and all the properties of the host galaxy, which, for instance, is not particularly forming efficiently stars at that moment, are well compatible with the merger scenario. It shows how characterizing the host galaxy is important to really classify gamma ray burst. And the idea is that with Eclair, we expect to better understand the fraction of short gamma ray burst which is extended emission, which is maybe much more frequent than what we think today. And the origin of the extended emission, I debated again. What is also interesting in this distribution is the fact that we detect a lot of soft or very soft gamma ray bursts, which were not well covered by past experiments. Already at least 4, maybe more. We can know that from the beginning with a quick look analysis. For instance, in this case, you see that it's detected only below 8 kV, maybe marginally below 20 kV, and not at all above 20 kV. So we can inform the community that we have a soft burst to favor an efficient follow-up. And I will show you an example where this follow-up worked very well. So it's a case where, again, as I told you, it's detected only below 20 kV, marginally between 20 and 50. It's a so-called X-ray flash, a very soft gamma ray burst. Interestingly, with our spectral analysis, we confirm that it's really soft and it's even maybe compatible either with non-thermal emission or with black body emission, which is interesting because maybe it says that it's not exactly the same mechanism as a standard gamma ray burst. The afterglow is very faint, but it's detected in X-rays, invisible with a follow-up by VT. And you see at the end a small rise. And this is the emergence of an underlying 1C broadline supernova, which has then been detected by GWST. And so clearly, it's related to some kind of collapsar, but it's not exactly the same as the standard gamma ray burst. And so we should have several events like that. We will characterize them. We will try to understand what they are. And this can be related to observation that we had already in the past at the time of BEPOSAX and ET2, which had already X-ray instruments. But at that time, the sample of well-characterized events was really low. I mean, well-characterized, I mean also including the afterglows, the host, and the redshift. We know that probably there is some diversity, and that, for instance, here is an example where probably it's not the same scenario as what I have explained initially, but the shock breakout, so a jet just emerging from the collapsing envelope of a massive star. There is a lot to learn. And again, this is where there is a synergy with the Einstein probe, because by definition, Einstein probe is detecting many of these events. So they are often qualified as fast X-ray transient before proving the association with gamma ray burst. But probably most of these events are soft gamma ray burst. And as I told you, SVOM will see less events than Einstein probe, but will characterize them. And there are many ideas for the physical origin. It can be either intrinsically soft, and then it says something about the continuum of events, or it can be off-axis events, or it can be something completely different. there is probably some diversity to explore. And I would like to mention something quite recent, which has maybe to do with that. It's not at all the same wavelengths, but you know that now with ZTF and soon Vera Rubin LSST, we have a large coverage of the variable sky in optical, and we start to detect so-called orphan afterglows. Afterglows which are detected directly by an optical telescope without a trigger by a gamma ray burst, just by following the sky, like it's done for supernovae. And what is very interesting is that before the first detection, we were expecting most of these orphan afterglows to be off-axis gamma ray bursts. So we do not detect the gamma ray burst because we are not in the right direction, but after the deceleration, we detect the optical afterglow. But in fact, a large fraction of this orphan afterglow looks like on-axis gamma ray bursts, which were very inefficient in gamma rays. And maybe this is extreme cases where it's even not soft, weak emission, but nothing. Maybe we are starting with different probes to really explore a new part of the gamma ray burst population at the low luminosity, low epic extremity. So I have almost finished. Of course, we detect also a lot of long gamma ray bursts, the main population, classical long gamma ray bursts. We have already 9 with the redshift and many more. So it means that we can still improve our efficiency for measuring redshift. We characterize them very well. I will just show a few examples. This one is very interesting because it's a very long one, more than 500 seconds. And thanks to a very fast slew, we catch the end of the prompt emission in X-rays and optical. So you see, it's very early data, so I'm sorry, it's not, but you see the decay in optical and then the rise of the afterglow, the same in X-rays. It's very rare to start observing before the end of the prompt emission, especially in optical. This transition from the prompt to the afterglow is not well described. The light curve is quite standard here for the prompt emission. So very interesting case. Another one which is really intriguing is this one. Again, an efficient follow-up. So you see here, this is time since trigger. You see the light curve in X-rays. We see very well the decay just following the prompt emission. Here it's difficult to say, maybe some kind of shallow phase or plateau, I don't know exactly. And then a more standard decay, which is detected thanks to Swift and Einstein probe. So quite a complex light curve. And a completely achromatic behavior. This is the same scale, invisible, so VT plus other instruments. You see just a rise with a peak, which is somewhere here, and then a decay, a very smooth light curve. It's very puzzling. Is it a slightly off-axis event? We don't know, but it's really interesting. And it shows, again, the quality of the VT light curve. And here, this is a zoom on this part with the French follow-up telescope Colibri. Here, it's another example of a follow-up by SVOM of a Swift burst. And here, it's a case where we started to observe 66 seconds after the trigger on board Swift. So it allows to have an impressive multi-wavelength data set, including a lat observation with Fermi, so in the above 100 MeV. And it allows to really test in details the physical modeling of the early deceleration with several kinds of shock in the outflow. And finally, I won't show the spectrum of our burst at Z equals 7.3, but it's not, if I understand well, a high SNR spectrum. We see mostly the Lyman break allowing to make the measurement of the redshift. So we should see that as a potential. The idea is to be even more efficient to observe spectroscopically much earlier. But already there are some things to learn. The fact that it was not detected by VT, but with very strong upper limit quite early. You see magnitude 23. And it's only with the near infrared, and by chance there was an instrument operating at the node at the right moment, that it was detected 12 hours after the burst. So imagine what could have happened if it was 1 hour after. And then the observation with the LTX shooter showing So we are sensitive to this population. We have to be more efficient to characterize it. I will conclude. Okay, so SVOM has started to explore the GRB diversity. We see very well the impact of several choices when we design SVOM in terms of spectral coverage, of optimization of the follow-up sequence. It's very encouraging. We have many papers in preparation to present this early detection. There is still a lot of work to do. You have noticed that I have not shown a joint spectral analysis with ECLAIR with GRM because cross-calibration is still ongoing. It's really, personally, something I'm really waiting for because it would be really a way to test physical models of the prompt emission, something on which we have worked a lot with Robert. But clearly, compared to Swift, SVOM can say a lot about the prompt emission with this combination and the fact that we have already a few events where we have led prompt observation with MXT and VT. So we will see. And then we are building a sample, and on a longer time scale, we will start population models, of course. So this is my conclusion. It works well. We are still on the learning curve, but it works well. And what is really satisfactory is a strong support of the SVOM partners and the GRB community. So we should have more results to show soon. Thank you very much.
Well, thank you, Frédéric, for the very clear and complete presentation. So, questions?
Thank you very much for the very interesting summary. What is the time resolution of SVOM? Is it comparable with, for instance, Swift? Or...
You mean for the prompt emission or for...
for prompt emission, yes.
So for the prompt emission, I don't know exactly, but we have, in fact, with the coded mass telescope, we have all events. So we can, each event is tagged with an arrival time with a sub-millisecond resolution. Then it's a question of signal to noise. So we cannot, we have to bin, of course, to see something. But it's comparable with Swift or Fermi for the bright event.
And I ask a very short question. What is the policy for the data? Because at the beginning, there was a much more, I mean, in the GCN, there was linked to a much more complete data. Nowadays, it's just one light curve. But
good question. And now I know I had the strange feelings that I had forgotten a slide. So I know which slide. So SVOM is not an observatory. So data belong to the collaboration. But on the other hand, obviously, for gamma ray burst, we have a lot of information which is made public immediately. So we had to put priorities. So the priority was to have the system of notices and circulars to emit alerts operational. So now it works. The next step, and it should be done before summer, is to give links in these circulars to access to early light curves and things like that. And then most of the products produced for gamma ray bursts will become public with such a system. But then it won't be event data with response matrices, things like that. So the idea is that to work really on data, on SVOM data, what is needed is an association with some SVOM COI, and SVOM is open to such collaboration. In fact, all the paper in preparation I have briefly flashed are paper which are in preparation with partners, with colleagues outside. It's not public.
Not like Swift.
Not at all, because it's not at all the same status. And there are, I mean, you imagine it's a Chinese-French project. There are documents describing exactly what can be done or not. And clearly, it's not an observatory. But it does not mean we are not open to collaboration at all. So it's just another way to organize, but it's possible to work on some data. Yes.
Yeah, thanks for the very nice talk, Frédéric. You're now a perfect observer.
Perfect, it's maybe too much. But I have entered a new club, yes.
A short question about the MEV background. How, as you know, it is the most difficult thing in the high energy astronomy because the detectors may be activated by energetic particles from the cosmic rays of the sun, and this may be variable depending on the solar activity. And I know that Bertrand Cordier has spent a large fraction of his career in trying to understand it. So how well do you know that?
So
how does it affect the spectrum you get?
Good question. In fact, when I say that we need experts to validate triggers, it's part of the job because in fact, we have launched SVOM in a period of high solar activity. So we have a lot of events related to the Earth's magnetosphere with the particle events, solar flares, etc. And we have to discriminate. It's not always easy, but we have many diagnostics. We have a particle monitor on board GRM. The fact that ECLAIR is a coded mass telescope helps also a lot because with images, we can do very well the difference between a point source or something which is more diffuse. But it's difficult. And on the other hand, I don't know if you remember when I have very briefly flashed the fact that we have some efficient quick look analysis pipeline. One of the models behind such automatic background fit cannot take into account a particle event or a solar flare. It's too difficult. So that's why sometimes we need a human being reprocessing data. But otherwise, it already takes into account what is known on the cosmic X-ray background. And there are several components, direct emissions, there is some scattering with the Earth's atmosphere, etc. It's not the same component dominating at each energy. And somehow we take that into account to have some kind of model because we know how the background should evolve during a slew due to the varying angle with the Earth, which is part of the problem. In the future, we hope, but we are not at that stage yet, to have some kind of physical model of the background. It has been achieved by Fermi GBM, so in principle, it's feasible with SVOM, but we are not at all at that stage. But we already take that into account partially, yes.
Frédéric, I have a question about timescales.
Timescales, yes.
At the very beginning, you showed a slide where initially it was optically thick. So
yeah, okay, yes.
When does it become transparent? And then the second phase where it hits the interstellar medium.
Yeah, this.
Yes, this one. And then there's another phase. Sometimes a supernova 1C appears. So what are the timescales for those events? Yes.
So the supernova is not on this plot because somehow it's another ejecta. The difficulty is that following the core collapse, maybe the ejecta responsible for the supernova is ejected very rapidly, but in fact, you know that supernova has different time scale with a rise, a peak, etc. So typically, we expect a supernova to peak maybe 2 weeks after the. So it's not on this plot. Here on this plot, it's really focusing on the relativistic ejecta responsible for the prompt emission and the afterglow. And here to answer in terms of time scale is difficult because, of course, it's not at all the same if you are in the frame of the relativistic ejecta or in the frame of the observer. So everything moves more or less at the speed of light. I have not given numbers, but typically gamma ray bursts have Lorentz factor above 100 initially. So it's really and so for the observer, typically between the moment where it becomes transparent and the moment where it could emit above the photosphere, the delay is maybe 1 second only. Then when do we expect the beginning of the deceleration? It depends on several factors, how much energy there is the outflow, what is the density of the external medium. But typically, the peak, the beginning of the peak and the beginning of the polar decay can be 1 minute, 2 minutes after the prompt emission. We have some cases now with them where the delay is much longer, and this is puzzling. Maybe it's an indication of axis view, I don't know. But it's extremely fast, you see. And that's why we need to have this very rapid follow-up. Yeah.
Can I add something on this?
Yes,
One very interesting case, or some interesting cases would be off-axis GRBs at low redshift, because in principle, then if it is a lot of axis, you should detect the supernova before the GRB. So in principle, you should have the one CBL supernova, and only after that, there should be a contribution of the afterglow, but it will be very faint, the afterglow, compared to the supernova. So there are research in this case, but they are done in radio. So to see if from the sample one CBL supernovae, if we detect the radio GRB afterglow, let's say.
and in the same spirit, there are a few GRBs with an associated kilonova, and the time scale for a kilonova is typically 1 week. But in the particular case of 170817, which was completely off axis, the kilonova was detected much before the afterglow, for a similar reason.
Thank you for your presentation. You've demonstrated that gamma ray studies, it's a big collaboration between a lot of laboratories. How would you describe the main specific contributions of SVOM in these studies? Is it the specific localization by eclairs and
Yes, this is maybe what I have tried to briefly flash at the end. I would say that compared to Fermi, we can localize. Compared to Swift, we have the coverage of the prompt emission, because the BAT on board Swift has a much narrower spectral range. And we extend this spectral coverage to 4 keV, which is really new. That's why we are sensitive to all this population of soft events, which is not well characterized. So these are first differences. And then compared especially to Swift, there are also different choices which have been made for the follow-up to try to improve it, the anti-solar pointing, things like that. And somehow it seems to work because we have a higher fraction of detection of afterglows and redshift measurement. So, but it's a difficult game, you have seen, so we're still to fully exploit that, but it's somehow we have tried to optimize many aspects, taking into account the experience of Swift.
The difference between with Swift, especially, is that SVOM can see in red, and this is very important, especially for high redshift.
Yeah, so you're right. I should have added that in addition, what is really new for SVOM compared to Swift is the sensitivity of the visible telescope. So with the X-ray telescope is less sensitive, but the visible telescope is much more sensitive, and as you just said, with a blue and a red filter. So, of course, you know that it's a very interesting indicator. For instance, if one afterglow is detected only in the red filter, it has to be taken with caution because it can be hints that we have a high redshift gamma burst. We know that in some cases it can also be related to intrinsic reddening in the host of the galaxy, but maybe not of the gamma burst, but maybe not so high redshift. But it's an information that it's interesting to know early to organize a follow-up, because in both cases the event is interesting. So yes, there are many aspects where we improve. Yeah. So at the end, to be clear, the sample won't be comparable in size with the sample of Swift. It's impossible. But I really think that we will be able to have a large added value for the characterization of this.
Any more questions? So if not, let's thank Frédéric again.